Ever catch yourself wondering what actually makes math tick?
Yeah.
And I don't mean like just solving for X, but like the real core ideas, the principles.
Foundation.
Yeah, the foundation that makes math, well, math.
Right.
And there's
Yeah.
exactly what we're diving into today, the fascinating world of
Yeah.
foundations of mathematics.
Yeah, a wild ride.
It really is. And it's a journey that, it's captivated mathematicians for centuries, right?
Oh, yeah.
From like the ancient Greeks trying to figure out what numbers are to like 20th century thinkers exploring the edge of what we can even know using math.
Yeah, what's knowable in math.
Yeah.
Absolutely.
So we're using Wikipedia as our guide for this deep dive.
Excellent source. Very thorough.
Oh, absolutely. And you'd be surprised
Yeah.
the questions that mathematicians have been kind of like wrestling with for like ever.
Oh, yeah. I mean, like, is math something that we just discover?
Oh, interesting.
Or is it something that we invent?
Whoa.
And
That's a big question.
It's huge. It has huge implications for how we understand things like computer science.
Yeah.
Physics.
Oh, wow.
Like the nature of reality.
The nature of reality.
Yeah.
Okay.
Big stuff.
So let's start way back up here. Let's go back to the ancient Greeks.
Okay.
They were really into logic and geometry.
Geometry.
And they built this whole system of mathematics that seemed,
it seemed pretty good.
for centuries, it seemed like rock solid.
Rock solid.
And at the heart of their system was this idea that all numbers could be shown as
ratios, like fractions, right?
Okay, so like give me an example.
Like comparing the length of one line segment to another.
Oh, okay.
Yeah.
So like I'm picturing like the classic like dividing a pie
Yeah, exactly.
into like even slices.
Yeah, you got it.
Okay.
But then they discovered something that like threw a wrench in the whole thing.
Oh.
Irrational numbers.
Okay. And irrational numbers, just a reminder, are
These are numbers that cannot be expressed as a simple fraction, no matter how hard you try.
Okay, give me an example.
Like the square root of 2.
Okay.
Very famous example. It's the length of the diagonal of a square with sides of length 1.
Okay.
And you try to write that as a fraction, you're going to be there for a while.
You're going to be there forever.
Yeah, exactly.
So what did the Greeks do?
Yeah.
I mean, did they just like throw in the towel? Were they like, all right, math is broken, we're done?
No, they were much too clever for that.
Okay.
So a mathematician named Eudoxus.
Eudoxus.
Yeah, he came up with this really clever workaround, a way to compare these irrational ratios without actually having to like define them as specific fractions. It was a big deal.
That's huge.
Yeah.
So they found a way to be like, okay, we can't define it, but we can still work with it.
Exactly. Okay.
Keep moving forward.
Okay. And it seems like that's a theme here, right? Like mathematicians, they hit a wall and they're like, all right, new concept. Exactly. New concept, new tool.
Let's do it. And that kind of reminds me of like when Newton and Leibniz came up with calculus.
Yeah.
Calculus is all about motion and change.
Absolutely. Yeah.
Powerful. But it introduced this concept.
Of infinitesimals.
Infinitesimals.
Yeah.
Okay. For those of us who, maybe haven't heard that term in a while, what are those again?
Okay, so imagine something that is smaller than any number you can think of.
Okay.
But it's not 0.
Okay. My brain is already hurting a little bit.
Yeah, they're very small. They're very, very tiny.
So it's like this idea
Yeah.
that's so small it almost doesn't exist, but it has to exist for math to work.
Yes, exactly. That's a great way to put it. And, they're really useful for things like, figuring out instantaneous velocity.
Yeah.
But they caused quite a stir in the math world.
Really?
Yeah, some mathematicians like George Berkeley, they weren't convinced that these infinitely small quantities were even logically possible.
So calculus worked.
Yeah.
But nobody really knew why.
That's right.
I bet that was frustrating for some people.
It fueled some very intense debates about the foundations of mathematics.
Oh, yeah.
Oh, yeah. But ultimately, these debates, they pushed mathematicians to think more rigorously about numbers and limits.
Right.
To move beyond just these, like, geometric ways of looking at things.
So it's like, it worked, but we need to, like, figure out why it works.
Yeah, exactly.
Okay.
We can't just be happy with it working.
Gotcha.
Yeah.
So that brings us up to the 19th century, which,
Right.
from what I've heard, it's a wild time.
It was a wild time for math, yeah.
For mathematics.
Yeah, the 19th century.
Okay.
They were really wrestling with these foundational issues, like on multiple fronts, right? And for one thing, they started exploring geometries where Euclid's postulates the ideas of, parallel lines never meet,
Oh, yeah.
all that stuff.
Yeah.
They started playing around with geometries where those things weren't necessarily true.
Wait, hold on. So you're telling me there are geometries where parallel lines do meet? Yeah.
That's right. Yeah, it's pretty wild.
How is that even possible?
It's total mind bender, but it's true. And they're called non-Euclidean geometries.
Okay.
And these geometries really challenge the idea that there's just one true geometry.
Right.
Like math could describe multiple equally valid realities.
Oh.
It really makes you question, like, what does it even mean for something to be true in math, right?
Right.
And if questioning the very nature of geometry wasn't enough,
Yeah.
mathematicians also started digging deeper into, like, the building blocks of math,
Okay.
the things we kind of take for granted, like, the natural number.
They're like 1, 2, 3.
1, 2, 3, and so on. Yeah.
Yeah, just like counting. I have to admit, like, I never really thought about there being different ways to like define numbers.
Yeah.
Like, isn't it just kind of self-evident?
You would think so, but it gets really tricky when you try to define even the simplest mathematical concept really, really rigorously.
Okay.
Like, what does it even mean for something to be a natural number?
Right.
And in trying to formalize these basic concepts,
Okay.
mathematicians started grappling with these even more abstract ideas,
Okay.
like, what is infinity?
Yeah, that's a good one.
This is a concept that's puzzled thinkers for, like, millennia.
Right.
Oh,
Forever.
Yeah.
Okay.
So math went from questioning geometry
Right.
to questioning numbers themselves.
Like an existential crisis.
It really was.
Right.
And just when they thought things couldn't get any weirder, along comes Bertrand Russell
Okay.
with a paradox that just, like, shook the foundations of mathematics.
All right, hit me with it. What was Russell's paradox?
Okay, so imagine a set
Okay, I'm imagining a set.
that contains all sets that don't contain themselves.
Okay.
The million-dollar question is,
Yeah.
does this set contain itself?
Okay, so if it does contain itself,
Yeah,
then it shouldn't,
right.
because it's only supposed to have sets that don't contain themselves.
Yeah.
But if it doesn't contain itself, then it should be,
You got it.
because it fits the criteria.
Exactly.
It's like a logical loop.
It's a total contradiction. It's
Yeah.
a mind bender.
Like, how do you even...
Yeah, and it revealed this flaw in set theory,
Oh, wow.
which at the time was like the most promising foundation for all of mathematics.
Oh, really?
Yeah, it was a big deal.
So what happened? Like, did that just blow everything wide open?
It caused a major upheaval.
Okay.
Mathematicians realized they couldn't just, like, sweep this paradox under the rug.
Right.
They had to address these really foundational issues.
Right.
And that's what they did.
Okay.
And from this period of crisis, different schools of thought kind of emerged, right?
Okay.
Each with their own, like, way of dealing with these really profound questions about, like, what is mathematical truth?
So it's like different schools of mathematics now, each with their own perspective.
Yeah, exactly.
Okay, so, like, give me an example. What's one of these schools of thought?
So one school of thought that emerged was formalism.
Formalism.
Yeah. And formalists, they believe that math is essentially a game.
Oh, okay.
Right. A game with symbols and rules and axioms.
So it's like, it doesn't matter if, like, I'm trying to think of an example, like chess.
Yeah.
It doesn't really matter if the pieces represent, like, a real army.
Exactly.
As long as you follow the rules of chess,
Yeah.
you can play the game.
The game makes sense, yeah.
Okay.
And so the formalists are like, the meaning or the truth of the mathematical statement. That's not really the important thing.
Okay.
What's important is it consistent within the system?
Oh, interesting.
As long as you don't run into contradictions, you're good to go.
Okay, so it's more about the, like, internal consistency of the system than, like, if it reflects something, like, real, necessarily.
No. Right. And then you have, on the other side,
Okay.
you have the intuitionists.
The intuitionists.
Yeah. They had a very different take on mathematics.
Okay.
They believed that mathematical objects and truth, they weren't things that we discovered out there in the world, Right.
They thought math is something that we construct in our minds.
Okay, so for them, it's more about, like, how our brains work than about some external reality.
That's a great way to put it, yeah.
Okay.
They emphasize this idea of, like, intuition and logical deduction in building up mathematical proofs.
Right.
And they were kind of wary of relying on these, like, super abstract concepts like infinity.
Okay.
They preferred to stick to things that we could, like, really grasp and build step by step.
Interesting.
Yeah.
It's wild that something as, like, fundamental as math
Yeah.
could have, like these totally different interpretations.
Right. It's all about perspective.
Yeah.
And just when you thought the dust was settling from that debate,
Oh, no.
a mathematician named Kurt Gödel, he comes along
Oh, boy.
and just like drops a bombshell that changes everything.
Okay, here we go. Another plot twist. Who is Gödel and what did he do?
So Gödel, he was working on these things called the incompleteness theorems.
The incompleteness theorems.
Yeah.
And they had to do with like the limits of what we can actually know within a formal system of mathematics.
Okay.
So imagine like a system like the one that Hilbert envisioned, where it's consistent, it's complete,
Okay.
it can prove all the true statements.
Right. So like Math-utopia, basically.
Yeah, Math-utopic. Right. Like every question has an answer.
Yeah.
Every true statement can be proven.
Yeah.
But Gödel kind of shattered that dream, at least partially.
Okay.
His first incompleteness theorem.
Yeah.
It states that even in a consistent system, like the one Hilbert imagined, there are going to be true statements that we just can't prove.
We can't prove.
Yeah.
So there are mathematical truths out there that we might never be able to definitively say, yes, that's true.
That's right. Yeah. It's kind of a mind-blowing and a little bit unsettling thought.
A little unsettling. What does that even mean for the field then?
It means there are like these inherent limits to what we can know, even in this like perfect logical world of math, you know?
Yeah.
Gödel showed that no matter how hard we try to build this perfect system of math, there'll always be these truths, like just outside, you know?
Just like out of reach.
Yeah, just out of reach, exactly.
Okay. So where does that leave us?
Right.
Like, did Gödel just like blow the whole field open?
Well, not exactly, and it's important to remember that, like, math still works, right? Like, bridges still stand up, computers still compute.
Sure.
We can still use math to, like, understand the world.
Right, right.
So it's not that he invalidated math. It's more like he just revealed this, like, deep truth about it, you know?
So it's like we thought we were playing a game where we would eventually learn all the rules and be able to solve every problem. Yeah. But Gödel's like, nah, some puzzles are just unsolvable.
Some things we just might never know,
That's kind of a humble
It is humble.
realization, but also like it opens up. It's like, oh, now there's even more to explore. Right?
That absolutely just makes it even more interesting.
Yeah.
Adds a layer of mystery.
Right, because if we could know it all, then it'd be, all right, we're done, everyone go home.
Exactly. Yeah, what's the point?
Yeah.
But this means there's always something else to figure out.
Okay, so after all of this, right?
Yeah.
Like we've gone through irrational numbers, infinitesimals.
We've been through a lot,
Non-Euclidean geometries.
That's a lot to take in.
Gödel's like mind-bending theorems.
Yes. Wow.
What are we taking away from this? Like, where are we?
I think the big takeaway is that math is just way more interesting than we often think it is, you know?
Yeah.
It's not just about like formulas and like solving for X.
Right. It's not just what they teach in school.
It's not just times tables. Yeah.
Yeah.
It's really about like the nature of truth and logic and the universe itself, you know?
So it's like math is like a language.
Yeah.
And we're like trying to decipher like the code of reality.
Exactly. Yeah. And what's really cool is that it has these real impacts, right? Like, like the foundations of math with this focus on like logic and formal systems, it really laid the groundwork for things like computer science.
Oh, that's true. Yeah.
Think about it. Like computers run on binary code.
Yeah.
It's all built on logic, on zeros and ones.
It's like without math, no computers.
Yeah, it's all connected.
That's why.
Without mathematicians thinking about this stuff,
yeah,
we wouldn't have the digital world that we live in.
That's amazing to think about.
Yeah.
That something so, like, seemingly abstract has had this, like, huge impact on our lives.
Yeah, and the story's not over yet, right?
It's true.
Like, mathematicians are still out there exploring these foundations.
Yeah, still searching, still trying to break the system.
Pushing the boundaries of what we know.
That's so cool.
Yeah.
So next time you know I'm using a calculator or something.
Yeah.
Or, like, writing some code, I don't know.
Everyday math?
Yeah, even just, like, looking at, like, patterns in nature. Like, I'm tapping into this, like, this whole legacy of like mathematical inquiry.
Totally. Yeah.
That just makes you appreciate
it's amazing.
the world differently.
Yeah.
It's like, oh, wow, okay.
Yeah, it gives you a whole new perspective.
There's so much more here.
Absolutely.
Than I realized.
Then who knows what we'll discover next, right?
That's the beauty of it, right?
Exactly.
Like it's never over.
The journey continues.
Well, on that note, I think we're going to wrap up our deep dive into the foundations of mathematics.
I think that's a good place to stop.
Yeah, it really is. But until next time, keep those minds curious.
Stay curious out there.